Time to learn more stuff about OpAmps before we have our lab on. So what we're going to be talking about today is common negative feedback OpAmp circuits. So in our last lecture regarding OpAmps, we focused primarily on the circuit analysis techniques involved to solve for the output voltage quantity. Today, we're going to be talking more about what OpAmps are practically used for, which is analog signal processing. So applying mathematical functions to waveforms. Okay. So the first OpAmp circuit that we're going to look at is this guy here. Where we are going to apply our input voltage, Vn, to the non-inverting input terminal. We are going to have a feedback resistor, which I'm generically going to call R2, connecting our inverting input to our output terminal. We're going to have a resistor here called R1 that's placed between the inverting input terminal and ground. Excuse me. And we are going to measure our output voltage at the output pin of the OpAmp. So to develop the relationships for these circuits, we are literally just going to apply that three-step process that we developed the last time we talked about OpAmps to figure out what these relationships are. Okay. So step one was to apply OpAmp rule number one: no current can flow into or out of our input terminals, and determine what the voltage present at the non-inverting input node with respect to ground is, which is what I'm labeling this voltage V+. Or I can also put it here. So what is V+ in this case? Vn, absolutely right. Okay. Our second step is to apply OpAmp rule number two, which says that no potential difference can occur across the input terminals of the OpAmp and determine the voltage V-. So if V+ is equal to Vn, then V- is equal to Vn. Absolutely right. Okay. Now we're going to apply Kirchhoff's current law at the inverting input node here. So effectively what I'm going to do, let me do this in, let's do this way. I'm going to take this current plus this current, add them together and set them equal to 0. Understanding that no current can branch off directly to the right and flow into the inverting input terminal. So if I do that, I get Vn over R1 plus Vn minus V out over R2 is equal to 0. And with a little bit of algebraic manipulation, which I'm not going to bother you guys with because we don't have a lot of time, we will find that V out is equal to a factor of 1 plus R2 over R1 times Vn. So this is how this particular circuit behaves. For your lab, I'm going to ask you to construct one of these, which I have done a terrible job of drawing over here. And I have one set up down in that corner of the room as well, which achieves a voltage gain of 3. So from that, if we wanted so let me talk about the concept of voltage gain actually, because you guys don't know what the hell that is just yet. Voltage gain, AV, is simply the ratio of V out to V in, which in this case would just be 1 plus R2 over R1. So if we want to make a signal larger, this is a good circuit to achieve that, okay? If we look at its voltage gain, AV will always be a positive quantity that is greater than or equal to 1, right? And we can determine how much larger than 1 it is by choosing the right ratio of resistances to bias our circuit. So if we wanted a voltage gain of 3, like I have achieved with the amplifier circuit that I constructed over in the corner there, that just means that R2 needs to be twice as large as R1, because I would have 1 plus 2 over 1 is 3. So that's how you get a voltage gain of 3. If you want a voltage gain of 7, then R2 just needs to be 6 times larger than R1, etc. So this type of amplifier is what's called a non-inverting amplifier. And it's called a non-inverting amplifier for 2 distinct reasons. The first of which is the input signal is applied to the non-inverting input terminal. And the second of which is because the output voltage has the same polarity as the input voltage. So if you put a positive voltage as your input voltage, you get a positive voltage at the output. The amplifier that we are about to look at has the opposite relationship. So before we move along from this guy, does anybody have any questions, comments, or concerns regarding the derivation of anything that we've done here? All right. So our second circuit is going to be very nearly identical to this one. Okay, there's one distinct and subtle change. So I'm going to take my op amp, and this time I'm going to ground my non-inverting input. I'm still going to have a resistor R2 providing negative feedback. I'm still going to have a resistor R1 over here. And I'm still going to take my output at this node. What I'm going to do differently is I'm now going to apply my input signal over here on the non-inverting input side. So if I apply op-amp rule number 1, says that these currents are 0 amps. What voltage appears at my non-inverting input terminal? 0 volts. What voltage appears at my inverting input terminal? All right. And so now I can apply KCL. Again, I'm simply going to add this current plus this current together. It's going to look like negative Vn over R1 minus V out over R2 is equal to 0. And with a trivial amount of algebra, that gives us the relationship V out is equal negative R2 over R1 V in. This particular amplifier, which will be the second part of your lab, has a voltage gain of V out over V in is equal to negative R2 over R1. So this amplifier is interesting. And the reason why I say that is because the previous example, we had a voltage gain that was always going to be +1 or higher, meaning it could only make signals larger, right? This particular amplifier can make signals smaller, so it can provide attenuation, or it can make signals larger, providing amplification. But I would say the trade-off here is that it can only do it while inverting the polarity of the input signal. Okay, so it gets an increased performance because it can both attenuate and amplify signals, but it also introduces a 180-degree phase shift between the input signal and the output signal, which means if you put in a positive input voltage, you get out a negative output voltage. Or if you put in a negative input voltage, you get out a positive output voltage. So this is called an inverting amplifier. Pretty much all of the other amplifiers that we're going to talk about today are effectively variations on these two topologies, okay? So before we move on to our next common op-amp circuit, anybody have any questions about this inverting amplifier? All right, so these two circuits are used to provide amplification or attenuation. So we are taking an input signal and we're either making it bigger or potentially making it smaller, all right? So we're just scaling our input signal by some factor. The circuits that we're about to look at perform more distinct mathematical operations. So we're going to learn about how to add signals together, how to take the difference of signals and things like that. So the first one of that vein that I want to look at is this guy. I'm going to call my feedback resistor, in this case, RF, and you'll see why I'm using that designation in just a moment. We're going to take our output signal here. But what we're going to do is on the inverting input signal side, instead of having a single resistor, which I'm going to call R1, we're going to have multiple resistors. Call this R2. Let's call this guy R3. We could have just two. We could have as many as we wanted here, but I'm just going to derive this for 3 particularly. And to give myself a little more room, I'm going to say that we have an input voltage VN1 applied across resistor R1, VN2 applied at resistor R2, and VN3 applied at resistor R3. So functionally, or at least based purely on looking at it, this looks very, very similar to our inverting amplifier that we just discussed, except that it has multiple input signals and multiple resistors connected to the inverting input terminal, right? If we were to approach this circuit using superposition, we could effectively just treat it as 3 inverting amplifiers added to each other, okay? We're going to approach it like we've done all the other circuits because I would like to be consistent, but there is a different way that we can analyze this and still get the same result. All right, so applying op-amp rule number 1, we have 0 amps flowing into or out of our input terminals. Voltage present at the non-inverting input is 0, which means the voltage present here at the inverting input terminal must also be 0 volts. And now I'm going to apply KCL and add this current plus this current plus this current plus this current together. And so what that's going to look like is negative VN1 divided by R1 minus VN2 divided by R2 minus VN3 divided by R3 minus V out divided by RF is equal to 0. And with a little bit of algebra, we would find that V out is equal to negative 1 over RF times VN1 over R1 plus VN2 over R2 plus VN3 over R3. Now we can't really define a voltage gain for this circuit because it has multiple input signals, okay? Effectively, what's going on here is that each input signal is being scaled by a distinct gain, right? So VN1 is being the scale, excuse me, that shouldn't be 1 over RF, that should be RF. My apologies there. Messed that up. Very, very sorry about that. So VN1 is being scaled by a factor of RF over R1. VN2 is being scaled by a factor of RF over R2. VN3 by a factor of RF over R3, etc. So what we call this is a weighted inverting summer because each individual input signal is being weighted by a different scaling factor, and it's a summer because we are adding all of the signals together. What if R1, R2, and R3 were all identical? So just as a quick aside here, if R1 is exactly equal to R2 is exactly equal to R3, then we would have V out is equal to negative RF over R1 times VN1 plus VN2 plus VN3. So all of the input signals would be scaled by the same factor. So this is just an inverting summer at this point because we're not weighting each individual input differently. So it's your 3 input signals get added together, and then that combination gets scaled by a factor of negative RF over R1. All right. For our next circuit, I'm going to apply a feedback resistor having a value, and I'm just going to call this R. I'm going to have a resistor between the inverting input and this node over here, which I'm going to call R. And I'm going to call this input voltage VN1. On the non-inverting input side, I'm going to have a resistor R like so. Another resistor R like so. I'm going to call this VN2. And for this particular circuit, it is important that all of our resistors are matched. They all need to be the same thing for this to behave the way that we want it to. Okay. So if I apply op-amp rule number 1, I have 0 amps flowing into my input terminals. This guy is a little bit more difficult than our previous few examples. What's the value of the voltage at my my non-inverting input terminal? VN2 over 2. Absolutely correct. Okay. So I have a simple voltage divider circuit attached to my non-inverting input node. So my voltage V minus, or the voltage present at the inverting input terminal, must also be 1/2 VN2. And now I can apply Kirchhoff's current law at my inverting input node. And so what that's going to look like is 1/2 VN2 minus VN1 divided by R plus 1/2 VN2 minus V out divided by R is equal to 0. Are we okay with that? So since I have a common denominator of 1 over R, I can just multiply both sides through by R, right? To clear that fraction. And then I have 1/2 VN2 plus 1/2 VN2, so a whole VN2 minus VN1 is equal to V out. So this is how we do signal subtraction. Okay. So the previous circuit was about adding signals together. This circuit subtracts signals, or takes the difference of them. Okay. So this is what's called a differencing amplifier. If the various R's or resistors that we use to bias this guy have non-equal values, we're still going to wind up with something akin to VN2 minus VN1, except that each of those input signals is going to be scaled by different factors. The math just makes it really, really ugly. So I would argue that if you ever wanted to scale the difference of a signal, take the difference and then apply that output of that to a different amplifier to scale the entire difference, as opposed to scaling each signal differently, because the math just gets real ludicrous real quick. All right. So we have performed now basic addition of signals and subtraction of signals. Multiplication and division cannot be done using a single amplifier, okay? But integration and differentiation can. So we can actually do calculus with circuits, which is pretty neat. These two circuits, the differentiator and integrator, are fundamental building blocks of control theory, communications theory, and filters. So they are integral to multiple aspects of electrical engineering. So our first circuit that we're going to look at is this guy. We are going to ground our non-inverting input. We're going to apply a resistor R as our feedback. And we're going to take our output voltage as a function of time at the output pin. And then what we're going to do here at the inverting input is put a capacitor. And let's call this Vn of t. Okay. So a couple of things here. First, let's remind ourselves of what the relationships for capacitor voltage and current are. So we know that IC of t is equal to C dV by dt. And we know that Vc of t is equal to 1 over C times the integral from negative infinity to t of IC prime d prime. So we're going to wind up using these relationships. Okay. Now, fundamentally, this is nothing more than an inverting amplifier, except that we've replaced one of our resistors with a capacitor. Okay. What I'm going to do here is I'm going to call, actually, I'm not going to use red because I've been using that color for other things. Green. So this is Vc of t, my voltage drop across my capacitor, where I've just chosen the positive polarity terminal to be on the left-hand side. Okay. And I'm going to call this current IC of t. Okay. And from here on out, we're pretty much just going to be applying those exact same relationships that we did previously. So we know that from op-amp rule number 1, both of these currents must be 0 amps. The voltage present at our non-inverting input terminal is 0 volts, which means the voltage present here at our inverting input terminal is 0 volts. And now we're simply going to apply Kirchhoff's current law, right? So I'm going to add this current together and this current together. And so that's going to give me negative IC of t, negative IC of t minus the out of t over R is equal to 0. So I'm going to do a little bit of algebra here. I'm going to move V out to the right-hand side and then multiply through by a factor of R. And so that's going to look like negative R times IC of t is equal to V out. Are we okay with that? Anything seem wild or crazy? So we know that IC of t is C dV, so I'm going to substitute that in. So negative RC dVc by dt is equal to V out. So the question then becomes, how are the quantity Vn of t and Vc of t related? Exactly right. Vc of t and Vn of t are literally the exact same thing because they're both the voltage measured between this node right here and ground. So we have a relationship negative RC d Vn of t by dt is equal to V out. So we're able to perform the derivative operation on a signal and then scale it by a factor of negative RC. Okay. So this is the differentiating amplifier. And our last circuit that we are going to analyze is then the integrating amplifier, which is effectively identical to the last one, except that we switch the position of the capacitor that should not be just a line. We switch the position of the capacitor and the resistor. So here's C. Here is R. Here's Vn of t. Here's V out of t. Just as a reminder, we know that IC can be expressed as C dV by dt. We know that VC can be expressed as 1 over C times the integral of IC t prime dt prime. So I'm going to label this voltage drop as Vc of t. And I'm going to label this current as IC of t. So applying op-amp rule number 1, we know that these currents are 0 amps. The voltage present at the inverting input terminal, excuse me, the non-inverting input terminal is 0 volts. So the voltage present at the inverting input terminal is also 0 volts. And we will now apply ACL at the inverting input node. So all of these derivations are carried out in literally the exact same way, doing that 3-step process that I detailed in our previous lecture. So we're going to have 0 minus Vn, so negative Vn of t divided by R plus IC of t is equal to 0. So I can say that Vn of t over R is equal to IC of t, right? Let's see. So IC of t Okay. So what I'm going to do now is I'm going to see what the relationship between VC and V out is. Anybody have any thoughts? VC is equal to negative V out. That's absolutely correct. And since VC of t is equal to 1 over, my stylus will write here, 1 over c times the integral from negative infinity to t of IC, I'm going to substitute in Vn of t prime over r et prime is equal negative V out of t. And then getting rid of the negative sign on the right-hand side, I get negative 1 over RC times the integral from negative infinity to t of Vn is equal V out. So that's how I perform integration using an op amp. It's just scaled by a factor of negative 1 over RC. So this is our integrating amplifier. All right, so these are the 6 different amplifier types that I expect you to be able to recognize on your upcoming exam 3, okay? Now, to derive the relationships that we got for all 6 of these amplifiers, we followed the exact same steps, right? Step number 1, apply op-amp rule number 1 and determine the voltage V plus. Step number 2, apply op-amp rule number 2 and determine the voltage V minus. Step number 3, apply KCL at the inverting input node. If you can do those 3 steps, you can solve any op-amp circuit that you will see in this class and the overwhelming majority of op-amp circuits you will ever see, because the overwhelming majority of op-amp circuits are negative feedback circuits, okay? So those 3 very simple steps are all you need to master in order to do all of your op-amp homework, all of your op-amp ICAs, all of your op-amp problems on your exam. Sound reasonable? All right, so that's enough out of me for today. I'll scroll back down